Hello, future engineers. This is 3D equilibrium of a particle, part 1. So there are 5 problems here, arranged according to level or degree of difficulty. So for the principles on 3D equilibrium of a particle, so if this is the particle, the equations will just be the resultant force is 0, and that implies that summation of forces, all components, x, y, and z must be 0. So I hope that uh, expressing a force in space as a vector in ijk form is no longer a problem. You can easily set up the vector form of a force so that you can easily add corresponding components and equate it to 0. So if you still have a hard time expressing it as a vector, I want you to review the previous videos on expressing a force as a vector. So for 3D force system in equilibrium of a particle, it implies that if the resultant force is 0 or summation forces is 0, the components Rx, which is summation forces x, is 0, Ry, summation forces y is 0, and Rz, summation forces along z equals 0. So because we consider 3D equilibrium of a particle, there will be no moment equation here because the resultant also passes through the point of concurrency. So just the three components must be equated to 0. So level 1 problem, the 5 forces act at end A of the boom. Determine T1, T sub 2, and T3 if the resultant of this force system is 0. So this is the figure. Then if you look at the figure, we can compute T2 right away if we sum up forces along Z equals 0 or RZ is 0. So for the solution, RZ is 0 equals T2 has positive Z component, T2 sine 30, and minus 20 equals RZ, which is 0. So T2 is 20 over sine 30, so T2 is 40 kilonewtons. Next, let's express T1 in vector form. It is directed backward and leftward. So T1 in vector form is magnitude of T1, quantity negative 6i minus 8j all over square root of 6 square plus 8 square. Simplifying, T1 is magnitude of T1 times negative 0.6i minus 0.8j. T2, which we have already solved in vector form, is equal to 40 quantity negative cosine of 30 degrees j along y and positive sine 30 degrees k along z. So simplifying, T sub 2 is negative 34.64 j plus 20k kilonewtons. Then T3, directed forward and leftward, is magnitude of T3 quantity 4i minus 8j square root over square root of 4 square plus 8 square. So simplifying, it is magnitude of T3 times 0.4472i minus 0.8944j. So we now reinforce Rx equals 0, and it is equal to for T1 negative 0.6 T1, and for T3 we have 0.4472 T3. So those are the only forces with x component. So equate to 0. So from here we can express T3 in terms of T1. T3 is 0.6 T1 over 0.4472. So it is 1.342 of T1. Then Ry equals 0. It is equal to 60, positive 60 here. Then for T1, we have negative 0.6 T1, 0.8 T1 rather. T1 times negative 0.8 J. Then for T2, we have negative 34.64. And for T3, we have negative 0.8944 T3. Since T3 is 1.342 of T1, so 0 equals 60 minus 34.64 is 25.36 minus 0.81, then minus 0.8944 of T3, and T3 is 1.342 of T1 from this equation. So therefore, we can now compute T1, 25.36 divided by quantity 0.8 plus 0.8944 of 1.342. So T1 is 12.68 kilonewtons. And finally, T3 is 1.342 of 12.68. So T3 is 17.02 kilonewtons. Level 2 problem. Determine the tension in each of the 3 ropes supporting the 600-pound crate. So again, let's express each force into vector form so that we can easily add the corresponding components and equate it to 0. So for tension in AB, it is directed forward positive 4I. So tension in AB in vector form is magnitude of tension in AB, quantity 4I. Then along Y, negative 4J, then positive 7K. All over square root of 4 square plus 4 square plus 7 square. So tension in AB, quantity 4I minus 4J plus 7K over square root of 4 square plus 4 square plus 7 square. So simplifying, this is the vector form, boldface, then magnitude 4 over 9I minus 4 over 9J plus 7 over 9K. So that is tension AB in vector form. Next is tension AC. It is directed backward, negative 4 along X, then leftward, negative 2 along Y, then upward, 7 along Z. So therefore, tension in AC is magnitude of tension in AC, negative quantity negative 4I minus 2J plus 7K over square root of 4 square plus 2 square plus 7 square. Simplifying, tension in AC is magnitude of tension AC, negative 0.4815I minus 0.2408J plus 0.8427K. And finally, tension in AD, it is directed forward, it is directed forward 1.6, then rightward 4, upward 7. So tension in AD is equal to tension AD quantity 1.6I plus 4J plus 7K over square root of 1.6 square plus 4 square plus 7 square. Simplifying, tension in AD is magnitude of tension in AD 0.1947I plus 0.4866J plus 0.8516K. So Rx 0 equals 4 over 9 tension in AB minus 0.4815 tension in AC, then plus 0.1947 tension in AD. Call that equation 1. 4 over 9 tension in AB minus 0.4815 tension in AC plus 0.1947 tension in AD equals 0. Then Ry equals 0 equals negative 4 over 9 tension in AB, negative 0.2408 tension AC, then plus 0.4866 tension AD. Call that equation 2. Then Rz is 0 equals 7 over 9 tension in AB, plus 0.8427 tension in AC, then plus 0.8516 tension in AD, then minus 600 here, the weight of the crate. So simplifying, 600 is 7 over 9 tension AB plus 0.8427 tension in AC plus 0.8516 tension in AD. Equation 3. Solving these three equations simultaneously by elimination, by substitution, or whatever available method that you're familiar with and you mastered, then we'll get tension in AB equals 166.8 pounds, tension in AC 269.4 pounds, and tension in AD 285.6 pounds. So this problem, level 3, should have been assigned to higher level, but with my explanation, I hope that you can still follow, even if this should be a higher level problem. Find the maximum load P that can be supported by the tripod if the force in any leg is limited to 2,000 pounds. Assume that the legs are two force bodies. So meaning to say, two force bodies means just like a member of a truss. So pin-ended at ends so that the forces will be directed along the axis of the legs. So first, let us express, we expect that each leg will be in compression. So let's express the force in vector form. We have PBA equals magnitude of force BA, and it is directed left because it is a compression force, leftward and upward only. So to the left, that's opposite to the y-axis, so negative 6J. Then upward along the z-axis, positive 8K over square root of 6 square plus 8 square. So FBA is, simplifying, FBA is negative 0.6, FBA times negative 0.6J plus 0.8K. Next is FCA, directed forward along X by 6 feet, so 6I. Then leftward along Y, so rightward because it is a compression member, so 3J along Y. Then upward 8 feet, so plus 8K over square root of 6 square plus 3 square plus 8 square. So FCA is, in vector form, is magnitude of FCA, quantity 0.5747I plus 0.2873J plus 0.7663K. So FDA is magnitude of FDA. It is directed backward by 6 feet, rightward by 3 feet, and upward by 8 feet. So negative 6I plus 3J plus 8K over square root of 6 square plus 3 square plus 8 square. So it's the same as that except for the X component. So FDA is equal to magnitude of FDA, negative 0.5747I plus 0.2873J plus 0.7663K. Then equate Rx0. So it is equal to 0.5747 FCA, then negative 0.5747 FDA. FBA has no X component. So that means FCA equals FDA equals FCA. So they are equal. Then Ry equals 0. Then we have negative 0.6 FBA here, plus 0.2873 FCA, then plus 0.2873 FDA. Since FCA equals FDA, so 0.6 FBA equals 2 times 0.2873 FCA because these two are equal from this equation. So we can now express FCA in terms of FBA. 0.6 over quantity 2 times 0.2873 is FBA is 0.9577 FCA. So since each leg is limited to 2,000 pounds, so FCA should be 2,000 pounds so that FBA will be less than 2,000 pounds, because if we set FBA equal to 2,000 pounds divided by 0.9577, then FCA will be greater than 2,000. So it contradicts with this statement here that each tripod leg, any leg is limited to 2,000. So we have the idea that for maximum P, then FCA should be 2,000, which is also equal to FDA, and FBA will be less than 2,000. So that's it. So if FCA is equal to FDA equals 2,000 pounds, then FBA will be less than 2,000. So that's correct because we maximize FCA and FDA, and FBA is only 1915 pounds. So next, RZ equals 0, then it is equal to 0.8 of FBA, which is 1915 pounds, plus 0.7663 of FCA, which is 2,000 pounds, plus 0.7663 of FDA, which is also 2,000 pounds, then minus P here. Then from here, we can solve for P. 0.8 of 1915 plus 0.7633 of 2,000 plus 0.7633 of 2,000. So the maximum load P is 4,585 pounds. Level 4. Determine the tensions in cables AB, AC, and AD. The figure shown. So again, let's express each tension in vector form. Let's begin with tension AB. So there's no axis, so you'll be the ones to provide the axis. So I'll choose this orientation, X, Y, Z, so that tension AB is magnitude of tension AB, quantity 3I minus 1J, then plus 4K over square root of 3 square plus 1 square plus 4 square. So simplifying, tension AB is magnitude of tension AB, quantity 0.5883I minus 0.1961J plus 0.7845K. Next, tension AC is tension AC is magnitude of tension AC, quantity negative 3I minus J, then plus 4K. So almost the same components except for the sign in the first component. So tension AC is magnitude of tension AC, quantity negative 0.5883I, negative 0.1961J, then plus 0.7845K. Then lastly, for AD, it is just 3J. So tension in AD is, in vector form, is magnitude of tension AD, quantity 3J plus 4K over square root of 3 square plus 4 square. So simplifying, that's tension AD times 0.6 J plus 0.8 K. And it's now complete. So set Rx 0. It is equal to 0.5883 tension AB minus 0.5883 tension AC only. There's no X component for tension AD. So that means tension AC is equal to tension AB. Then Ry equals 0. So we have negative 0.1961 tension AB, then negative 0.1961 tension AC, and zero point 0.6 tension AD along Y. So since tension AC is tension AB, so tension AD therefore is 0.1961 tension AB times 2 divided by zero point 0.6. So tension AD is equal to 0.6537 of tension AB. Then finally, RZ is 0, and it is equal to 0.7845 tension AB plus 0.745 tension AC, then plus zero point 0.8 tension AD, then don't forget minus 100 here downward for the load. And take note that these two can be combined because they are equal. And substitute the value of tension AB also. So 100 is equals 2 times 0.8745 tension AB plus zero point 0.8 of 0.6537 tension AB. So we combine these two because these two are equal, so times 2. Then 0.8 of tension AD, and AD is 0.6537 tension AB. So tension AB can now be computed 100 divided by quantity 2 times 0.7845 plus zero point 0.8 times 0.6537. So tension AB is equal to tension AC 47.8 pounds, and tension AD is 0.6537 times 47.8. So tension AD is 31.25 pounds. The square steel plate has a mass of 1,800 kilograms with mass center at its center G. Calculate the tension in each of the 3 cables with which the plate is lifted while remaining horizontal. So again, we have to select a set of axes here so that we can analyze it well. So for tension AD, it is in vector form. Tension AD is magnitude of tension AD. Then let's just make this in meters. Tension AD in vector form is magnitude of tension AD. Then quantity negative 1.2 I, positive 1.2 J, then positive 2.4 K. So AD is directed backward 1.2, rightward 1.2, half of 2,400 or 1.2 meters, and upward 2.4 meters. So that's why tension AD in vector form is magnitude of tension AD negative 1.2 I plus 1.2 J plus 2.4 K over square root of 1.2 square plus 1.2 square plus 2.4 square. Simplifying, tension AD is magnitude of tension AD times negative 0.4082 I plus 0.4082 J plus 0.8165 K. Next, tension BD, backward 1.2, leftward 1.2 meters, then upward 2.4. So it's the same except for the second component. So tension BD is magnitude of tension BD quantity negative 1.2 I, negative 1.2 J plus 2.4 K over square root of 1.2 square plus 1.2 square plus 2.4 square. So tension BD is magnitude of tension BD times quantity negative 0.4082 I, negative 0.4082 J, then positive 0.8165 K. Lastly, for tension CD, it is just forward 1.2 I, upward. So tension CD is magnitude of tension CD quantity 1.2 I plus 2.4 K over square root of 1.2 square plus 2.4 square. Then simplifying, tension CD is magnitude of tension CD times quantity 0.4472 I plus 0.8944 K. Then set Rx 0, then it is equal to negative 0.4082 tension AD, negative 0.4082 tension BD, then plus 0.4472 tension CD. So call that equation 1. Ry is 0, and it is equal to positive 0.4082 tension AD, negative 0.4082 tension BD. This one has no Y component. There's no J here. So that means tension BD is equal to tension AD. Substitute in equation 1, then we have 0 equals negative 0.4082 tension AD minus 0.4082 tension AD because we replace BD by tension AD plus 0.4472 tension CD. So here we can express tension CD in terms of tension AD. 2 times 0.4082 divided by 0.4472. So tension CD is 1.826 tension AD. Then finally RZ is 0 and it is equal to 0.8165 tension AD times 2 because we have another 0.8165 tension BD and BD is equal to tension BD is equal to tension AD. So that's why we multiply it by 2. Then plus 0.8944 tension CD, which is this, and tension CD is 1.826 of tension AD from this relation, then minus the weight of the steel plate, which is 1,800 times 9.81 to express it in newtons. So therefore, tension in AD is 1,800 times 9.81 divided by quantity 2 times 0.8165 plus 0.8944 times 1.826. So tension in AD is equal to tension in BD from this equation 5406 newtons. Then tension in CD is 1.826 times 5406. So tension CD is 9871 newtons. So that's it for this part 1.